Okay, now on with the demonstration. Hopefully I'll speak loud enough that you can hear me over the fans running to keep everything cool. First I'm going to go ahead and start with the power supply or the battery charger to show you what the output is on it. And it's reading approximately 50 amps coming out of the power supply, and that's so that we can get the voltage up to 12 volts. When I do the test, I'm going to go ahead and shift it up into the next higher setting so that we get closer to 13 volts. I think that gives you a better idea of the overall performance of the equipment, because it's designed to go on a car, and that's normally what power we have available is 13 volts. So I will also show the temperatures as we go around. Let me turn this back down, and I'll turn that back up before we continue on with the timed part of the test or the presentation. Coming around here, I wanted to start out with a battery. I put a battery in the system. It makes a lot less work on the battery charger sitting next to it, and it seems to just smooth out the operation and give a more realistic as to what it's going to be like on the actual car. But let me start out with ambient temperature here. Let's see, we are at, it is 86 degrees in this room right now, and the system's fully warmed up. It's been running off and on all day really, but it's fully warmed up now, and it's at 91 degrees. So the battery, is getting a little bit of heat there, but it's very controllable. Coming off the battery, I have number 8 gauge wire, and that's because we're actually, moving 50 amps over to the power supply. We're not actually using it, but we need it to convert it into a higher voltage. But I just wanted to show you that these things are just, all the connections, if done properly in this system, produce no heat. So it's actually a bit safer because you don't have any hot wire issues. That is, if everything is connected correctly. For instance, the only quick disconnect I've found that transmits no heat, or there's no heat loss, is 2 lugs and a bolt. There's no heat there. And I'll give you a temperature reading of that as well. So we're about 92 degrees on those lugs. So they're not hot at all. So from there, we move over to the power supply. This power supply takes in, like I say, 50 amps at 13 volts DC, and it modifies the current to 48 volts. Coming out the other side is 48 volts, and when I show you the cell, you'll see what the amp draw, or in this case the amp loss in the cell is. But let me just take a quick reading of the thermal cutoff. It's at 95 degrees, and there are several components inside this box. A lot of it has what I have found here is the compatibility of different boards or modules from different manufacturers that seem to work well together, along with the cell setup that I have. I wouldn't say it's anomalous, but it's definitely unusual. I've had several electrical people look at this, electrical contractors and people that work with, setting up motors and various things, and best they can say, this thing functions very oddly. It seems to be doing most of its work with voltage rather than amperage, which is pretty much backwards as to what everybody, as the way things are, as what we know right now. Anyway, so from there, I'm going to just move through the rest of the wiring and show you where these wires go. There's a plug right here that comes out of the power supply. There's a number of wires on here that are basically peripherals for the system. Low water lights, switches, and stuff like that. But these two wires here, which are 16 gauge, are the positive and the negative to the cell, and I'll walk around there in a second and show you where they connect up into the cell. But as you can see from the gauge of this wire, this is definitely not hot. There's really no temperature here. We're looking at 90, 91 degrees going through that wire. Like I say, the system's fully warmed up. So there's obviously not 50 amps going through that wire. Much less than that. Now there is this white wire right here is the basically the switch wire that runs to the power supply that turns the relay on. This black wire right here is the ground of the fan. I wanted to show some temperatures here. This is one side of the cell. This thing is, like I said, it's operating right now. I'm going to go ahead and take a reading of this tank. This is like, I call it the accumulator tank because it accumulates everything. Water, electrolyte, gases, and then it sends it off in the right direction. Anyway, we're at 110 degrees in the accumulator. The cell, which is air-cooled, I'm going to take several readings on it. On the cool end, we're at 108. 108. On the heat sinked portion, which is where the heat comes from, we're at 116 is the high reading. That's what I usually go with. And then on the hot end, it is approximately 134, 135 degrees. And that's about optimum temperature to make this, what we call EEW, I think, is the unusual gas that we're making. This other tank here is the expansion tank, and there's a little pointer there. That's the expansion tank. As most of you know, when gas starts to form in these cells, it expands by about a third. So that absorbs all that extra expansion when the system fires up. Hopefully, I'm not a very good cameraman. I apologize for the production qualities. I've spent most of my time working on the equipment and not trying to show it to anybody. So, from this angle, I wanted to show you what the rest of these wires do. I've got it set up to show the voltage here at 46.3 volts, and obviously the wires, that's the positive side of the cell over there, and the negative side is going up to right there. And in order to get a amp reading on the cell, what I've done is I've disconnected one of the lugs on the cell and hooked this alligator clamp, which is hooked to this amp meter, and so it just loops through the amp meter and back over to the cell. And that comes through just a 3-conductor universal type plug there. And this wire here is the positive for the fan. Basically, when you turn the system on, you get 12 volt DC to that connector to run a fan, or I also have a large blower that hooks to it with a relay. And as you can see right now, it is at about 11, almost 12 amps. Now I'm going to shift gears here and get ready to do the test. And it's at 11. Right now we're at 11 point. Oh, just came up to 12. We're right at 12 volts, 11.9, 12 volts. And I'd really like to do the test at 13. So I'm going to go ahead and shift gears up one setting on the. So we're at 12.5, and we've come up maybe about a half an amp on the amps going into the cell, and we're at 47.3 volts. So I'm going to go ahead and set the camera down, and I'm going to do 3 timed fill-ups of that bottle. It's a 500 milliliter bottle in there. I want to get it just so you can see everything just correctly there. And it should take anywhere from 9 to 13 seconds. I say the system produces 2.8 liters per minute, give or take a few points. So here we go. Dry off the timer here. Okay. And here we go. Okay. So, let me, if you could see that there, I brought this light in because I thought it might help. We are at 12 seconds. Do another one. Okay. And go. And that one was 11 seconds. You see that there? 11 seconds. It's the smaller of the two numbers. And one more time. Go. Oh, wait, I blew it. Sorry, let me start over. And go. Kind of blew it on that one, but I won't bore you with any more tests. You can see obviously we're right around 10 seconds. This one's at 12. So 10 or 11 seconds, 10, 11, 12, right in that area. You can see that, 12. So we're at, you know, right around 2.8, or let's say, yeah, 2.8 liters per minute is what I usually tell people. So anyway, that's my demonstration. I hope it creates a lot of questions for us to answer in the next part of the presentation. So on with the show.